Hi, this is week 29 of chemistry, and we'll be looking at the second lesson of Unit 6, which is chemical thermodynamics. In this lesson, for our agenda, we have thermochemistry as well as heat transfer problems. Our lesson objectives: students will learn how to calculate the amount of energy needed to raise the temperature of different substances. Let's get started.
Let's begin our lesson on thermochemistry by talking about specific heat. And before we actually get to the definition on the slide, let's talk a little bit about the pictures. On the picture on the left, you see a leather chair. On the picture on the right, you see a chair, car chair, that has cloth. That's a material for them. Now, if we were to put both cars out in the sun, and then one of those hot days where you can get like 102, 103, and both cars are out there for a couple of hours, and then you're asked, okay, which car would you rather drive in to go somewhere? And leather seats or cloth seats? Everyone would say, well, I'd rather sit on the cloth seat. It feels much cooler. Now, question is, if both cars were out in the sun for the same amount of time, then why does one seat feel hotter than the other? All right, the answer to that question has to do with how a material reacts to heat. Specifically, we're talking about the specific heat of the material. A substance like leather would have a very small specific heat. That means that only a small amount of energy will go ahead and heat it up. On the other hand, the cloth seed would have a very large specific heat. That means you need a lot of energy to get it to heat up. So that's why you feel that temperature difference. Now, the slide states that the specific heat of a substance is the heat required to raise the temperature of that substance of 1 gram of that substance by 1 degree Celsius. That's the actual definition for specific heat. So essentially, different materials react differently to heat. Now, energy transfer can be calculated using this equation. We have Q equals M times delta T times C. All right, so let's talk a little bit about the equation. What is Q? Q is the energy measured in joules. M is mass measured in grams. Delta T is change in temperature, so it'll be final temperature minus initial temperature. And C, and sometimes spelled C with a little p at the end, a little subscript p, that is referred to as a specific heat. Now, in the picture right there, we can see how different materials react differently to heat. And you see the picture, we have a gold bar next to a container with water in it. Both have the same mass, 1 kilogram. And if we expose them to the same amount of heat, represented there by the match on both sides, then what you're going to get is they're going to heat up to different extents. So, for example, on the left-hand side, the gold, we notice that the bar from the temperature raised all the way to the top at 90 degrees Celsius versus the bar for the water only raised slightly above the 20. So water heats up a lot slower because it has a much higher specific heat than does gold. Now let's break down the formula a little bit. In this slide, we can go ahead and get into what is Q. Q is energy measured in a unit called the joule. Now, if you're not familiar with joules, that's mainly a unit used for science. People are used to energy being measured in calories, particularly when we're talking about food. Now, if you drink a soda and you look at the label, you know that it's going to give you energy. How much? Usually 100 to 120 calories worth of energy. Now, same thing for the joules, just a different unit for energy, just like the calorie is. Very much like in temperature, you can have temperature in Celsius or in Fahrenheit, and they both tell you the energy, the temperature. Same thing for joules and calories, they both tell you the energy. All right, the mass is measured in grams. The delta T, the triangle is pronounced delta, it means change in temperature in Celsius. And that is temperature final minus temperature initial. And the last one, C, is called the specific heat measured in joules per grams times degrees Celsius. All right, so that is our equation. Lastly, a quick discussion on units before we get into some problem solving. All right, let's start with the calorie. Back in the day, calories, when you had a kilocalorie, that means 1,000 calories, you used to spell it with an uppercase C, as you see at the very top of the screen. All right, so an uppercase C for this one would mean 1,000 calories with lowercase c. So that was your relationship. Though that became a little bit of an obsolete way of doing it, because what happens if you wanted to use the lowercase c, but you wanted to write a sentence starting with that, then you would capitalize it, so that's an issue. So now what we use instead of uppercase C is the kilocalorie, so you see it right there, and they're both lowercase c's on both sides. So 1 kilocalorie is the same thing as 1,000 calories. Let me go ahead and jump down all the way to the bottom, and here kJ, 1 kilojoule, is the same thing as 1,000 joules because a kilo means 1,000. All right, now what is the relationship between calories and joules? That's here in the middle. For every 1 calorie, there's 4.2 joules. That's been rounded off slightly. It's really 4.184, but we'll round it off to 4.2 joules. And then the last one we haven't talked about, 1 kilocalorie has 4,200 joules in it. All right, so this is some relationship between calories and joules and kilocalories and regular calories. All right, now let's go ahead and solve some problems using the equation to figure out how much energy is being transferred.
Let's go ahead and solve example 1. Here we ask the following question. How many joules are required to heat 700 grams of nickel from 22 degrees Celsius to 322 degrees Celsius? And the specific heat of nickel is 0.44 joules per gram times degrees Celsius. So we're giving all that information. We're just going to go ahead and plug it into the formula. We're looking for the energy, how many joules of energy are required. We have the mass is 700 grams. The change in temperature, remember, is just final temperature minus initial. Here the final temperature is 322 minus our initial temperature of 22 degrees Celsius. And finally, the last digit is our specific heat. So we're just going to go ahead and plug them in and solve. So let's go ahead and do that. Q is equal to the mass, which is 700 grams. The change in temperature, again, is just final minus initial. So the final temperature was 322 minus 22, which is our initial temperature. That gives us a change in temperature of 300 degrees Celsius. We're going to all multiply times the specific heat of this metal nickel, which is 0.440 joules per gram times degrees Celsius. Notice that the grams and the degrees Celsius will cancel out, leaving behind just joules as our only unit. So to solve this problem, all we have to go ahead and do is multiply across, and that's going to go ahead and give us our answer. So it's going to be 700 times 300 times 0.44 gives us an answer of 92,400 joules. Now, sometimes when students solve this and they check the back of the book for the answer to see if the answer is correct, it might see the same number, but perhaps in a different unit. If this answer were in kilojoules, then it will look like this. 92.4 kJ if we're kilojoules, because you get this value divided by 1,000 to change it into kilojoules. Nevertheless, that's our answer for example number 1. Let's go ahead and move along into example number 2. In example number 2, it says the specific heat of water is 4.2 joules per grams times degrees Celsius. A sample of water with a mass of 25 grams has a temperature of 110 degrees Celsius. If 1,260 joules of energy are supplied to the water, what will be the final temperature of the water? So now we're looking for the final temperature, slightly different. I'm going to use the same formula though. Alright, so our first job is going to go ahead and be to isolate the change in temperature, since we're going to need that to solve for the final temperature. Alright, so I have an M and I have a C right here. So I'm going to divide both sides by m-C, and that will cancel it out, giving me the following formula. Delta T is equal to Q over mc. Alright, next, what is delta T? That's a change in temperature, which is really temperature final minus temperature initial. So I'm going to go ahead and substitute that. Temperature final minus temperature initial is equal to Q over mc. Next, what we're going to do, we're solving for Ti. So we need to get rid of, we're solving for the final temperature, Tf. So we're going to move the Ti over to this side. And notice how it's a negative. So once you move it to the other side, we're going to do it by addition. So we end up with final temperature is Q over mc plus Ti. That's going to be our formula to solve for the final temperature of the substance. So I'm going to go ahead and erase and work for that to give myself a little bit more room to work. So it's going to be final temperature is equal to Q. Q is the energy in joules. So out of all of these numbers, there it is. There's our Q, 1260 joules. So we're going to go ahead and put that in the numerator, 1260 joules. The denominator, we have the M, which is, the M is our mass in grams. So when you look in here, you see that 25 grams. That's what goes right there. So it's going to be 25 G. Next, the C is the specific heat. You see it right here, it's labeled the specific heat for the substance is water. So we look for it, and there it is, 4.2 joules per gram centigrade Celsius. It was given to us, though it is not always given to you. You're expected to memorize that one substance, the specific heat of water, 4.2 joules. All right, so we're going to go ahead and write that down, 4.2 joules per gram times degrees Celsius. And all this is going to be plus the initial temperature. We started at 10 degrees Celsius. So that is, there we go. That is the setup. So we're going to go ahead and work this out, and then whatever answer we get, we're going to add it plus 10 degrees Celsius. That's going to be our final answer. So anytime you got two numbers in the denominator, be sure to put parentheses around them when you put them into your calculator. So it's going to be 1260 divided by, open parentheses, 25 times 4.2, close parentheses, so put it around it, equal, it gives me 12. So I get TF is equal to 12 degrees Celsius plus 10 degrees Celsius. So give me a final answer of 22 degrees Celsius. And that is our answer for example 2. Let's go ahead and move along now to example 3. In example 3, we're asked the following questions. How many joules are needed to raise the temperature of 20 grams of water from 12 degrees Celsius to 25 degrees Celsius? And again, they're given us the specific heat of water, which is 4.2 joules per gram degrees Celsius. All right, so we're going to go ahead and solve it. This will be a lot like example 1, where we're just solving for Q. So we don't really need to manipulate the formula like we did in example 2. We can just go ahead and plug in the values that are given to us. All right, so we're going to go ahead and do that. Q is equal to the mass. In this case, it said it was 20 grams of water, so I'm going to substitute that where the M goes. Change in temperature, we're going from 12 to 25 degrees. So it is the final temperature, 25, minus the initial temperature, which is 12. So 25 minus 12 gives us 13 degrees Celsius. And the specific heat of water, which is 4.2 joules per gram degrees Celsius. All we got to do is go ahead and multiply across, and we'll get our answer. So it's going to go ahead and be 20 times 13 times 4.2. That's going to go ahead and give us 1,092 joules. All right, and that is our answer for example 3. All right, next one, example 4. In example 4, it says a sample of lead metal with a specific heat of 0.103 joules per gram centigrade Celsius at 25 degrees Celsius. All right, so there we have the specific heat and our initial temperature of 25 degrees Celsius. Next, they say after you add 78 grams of energy to the metal, the temperature increases to 75 degrees Celsius. What is the mass of this metal? So we're looking for the M in this scenario. So let's go ahead and isolate it from the formula. So our formula is Q equals M times delta T times C. So we're going to go ahead and divide both sides by delta T and C. And what that's going to go ahead and do is going to isolate the M for us. All right, so I'm going to go ahead and erase the delta T and the C because they got canceled out. And there's our formula. All right, so I'm going to go ahead and substitute the values in. Q, remember, is energy in joules. So when you look in here, you actually go to that 78 joules, because joules is the energy measured in joules. That's the symbol for it is Q. So I'm going to go ahead and put 78 joules divided by change in temperature times the specific heat. The change in temperature, it started at 25 degrees Celsius and it finished at 75 degrees Celsius. So you subtract them, 75, which is our final, minus 25. That's a change in temperature of 50 degrees Celsius. And the specific heat was given to us at 0.13 joules times grams times degrees Celsius. All right, again, we got two numbers in the denominator, so you always want to put parentheses around them when you plug them into your calculator. So I'm going to put 78 divided by, open parentheses, 50 times 0.13, close parentheses, equal, and we get our answer of 12 grams. And that will be the answer for this problem. All right, and that is example 4.
Next, we're going to go ahead and talk about energy being transferred between two different materials. So we're going to call it heat transfer. So the amount of energy transferred in a reaction can be calculated by that equation on the bottom, where M is mass, C is specific heat, Ti is temperature initial, and Tf is temperature final. All right, but this relates to when you have two materials that they're in contact with each other and one material is transferring heat from one to the other. The picture right there, we have a horseshoe that is very hot being dipped in water. So that would be the equation that we're trying to use for that at the bottom, where one element, in this case the horseshoe, is transferring heat to the water in the bucket. All right, so the color coordination here in red, you have, that's where you would put the material that is warmer. So the mass of the horseshoe would go there, the specific heat of the horseshoe would go there, temperature initial and temperature final of the horseshoe would go there as well. Now, notice that it's Ti minus Tf because the horseshoe starts at a higher temperature, so the initial temperature is higher, and then it finishes at a lower temperature. So therefore, you end up with a positive answer for the delta T when you subtract Ti minus Tf. On the right side of the formula, you have the mass of the water, the specific heat of the water will be the C in blue, and notice that is Tf minus Ti. Backwards from the left side in red, which is Ti minus Tf, on the right side is Tf minus Ti. All right, why is it backwards? Again, we want to have a positive value for the delta T, so temperature final would go ahead and be higher than the temperature initial. See, the water started off being cold. Once they put the horseshoe in it, the water heats up. So that's why the final temperature is higher than the initial. All right, so setting it up that way, you always end up with positive values for the delta T's. All right, now let's go ahead and move along to some practice problems.
Let's go ahead and take a look at example 5. Here we ask the following question. It says, a 25 gram sample of aluminum at 90 degrees Celsius is dropped into 100 grams of water at 20 degrees Celsius. What will be the final temperature of the system? Now, both the metal, the aluminum is placed into hot water. Both of them will reach the same final temperature. So they refer to a system as both of them put together. Given to you all the way at the bottom of the problem is the specific heat of the aluminum, which is 0.9 joules over grams centigrade Celsius. Now, not given to you is the specific heat of water. You're expected to know what that is. The specific heat of water is 4.2 joules per grams times degree Celsius. So remember that number. Now, for the formula for heat transfer, again, Tf on the left side and the right side are the same value. All right, now, the way I have this equation set up, I use a little bit of color on it. Red signifies whichever one of the two began, that is the warmer of the two. In this case, the aluminum sample started at 90 degrees, so all the information for the aluminum will go on the left-hand side. On the other hand, the water started at 20 degrees, that's much cooler as compared to 90, so the cooler, whichever is cooler of the two, is going to go ahead and go on the right-hand side. So all information for the water, we're going to go ahead and put it here. All right, so let's go ahead and again read the problem while at the same time writing all the information. A 25 gram sample of aluminum at 90 degrees Celsius. So that's for the left hand side. M is 25 grams and Ti is equal to 90 degrees Celsius. Is dropped into 100 grams of water at 20 degrees Celsius. So here's the water. Mass of the water is 100 grams of water, and our initial temperature of the water is 20 degrees Celsius. Next, what will be the final temperature? So we're looking for the Tf, and the very last part, the specific heat which is needed for the aluminum is 0.9. So I'm going to write that down. C equals 0.9 joules per gram centigrade Celsius. For specific heat of water is not given. It's one of those values that students are expected to have memorized. It is 4.20 joules per gram centigrade Celsius. So that's all the information we need. Now we just need to find for Tf, the final temperature, both of them put together, the final temperature of the system. So let's go ahead and work on that. Let's substitute all these values in to the formula. Again, all of this information for the metal goes on the left. Information for the water goes on the right. Again, the metal was hotter, and that's why it goes on the left. The water was cooler at 20 degrees. That's why it goes on the right. All right, so let's go ahead and plug them in and solve. So we're going to go ahead and begin with, on the left-hand side, 25 grams. All right, so it's a mass specific heat of 0.90 joules per gram centigrade Celsius, multiplied times Ti, which is 90 degrees Celsius, minus Tf, which is what we're looking for. And over on the right-hand side, here comes all information is going to go here. Mass is 100 grams, multiplied times the specific heat of water, 4.20 joules per gram centigrade Celsius. Temperature final we do not have, that's what we're looking for, and initial temperature is 20 degrees Celsius. Alright, so that is the setup for this problem. From here now it's just really simplifying it using your math skills to go ahead and solve for that TF. That is the same on both sides. Alright, so I'm going to go ahead and do this. I want to simplify it a little bit by just multiplying both of these numbers. So it's going to be 25 times 0.9 gives me 22.5. 22.5, 90 minus TF. And here 100 times 4.2 is going to give me 420 TF minus 20 degrees Celsius. Alright, what am I going to do next? Just keep on simplifying a little bit. I'm going to go ahead and distribute these numbers. And after I distribute them, we're going to go ahead and keep on simplifying as much as possible. Alright, so it's going to go ahead and be 22.5 times 90. So we're distributing the 22 to the 90 and to the TF. So we're going to end up with, here it is, 2025 minus 22.5 TF. That's after I distributed this 22.5 to the 90 and to the TF. Here we're going to do the same. It's going to be 420 TF minus 8,400. Alright, after we distribute the 420 to the contents of the parentheses. What comes up for us next? We're going to go ahead and combine like terms. So you see this has got a TF and a TF. So we're going to move this one over here. And notice because it's a negative, we're going to go ahead and move it over by addition. Same thing, we're going to go ahead and combine like terms. And that's a negative, so I'm going to go ahead and add. So I'm going to add 22.5 TF to both sides. So that's going to go ahead and give me 442.5 TF. And I want to go ahead and add 8,400 to the 2025. That's going to go ahead and give me 10,425. Final step, I just want the TF all by itself. So I'm going to divide both sides by 442.5. So I'm going to go ahead and show the work for that. 442.5. Giving us our TF. So that's going to go ahead and be, we're going to round it up slightly to 23.6 degrees Celsius. And that is our answer for the final temperature of the system. A couple of follow-up questions. Why is it that the metal dropped so much from 90 all the way up to 23, but the water only went up 3.6 degrees from 20 to 23? Why is there such a difference? So there's two reasons for that. Number one is the mass. The mass of metal is only 25 when compared to the water, which is 4 times as much water. That's reason number one. Reason number two also has to do with the specific heat. The specific heat of the metal is very low at 0.9. That means that its temperature fluctuates quite a bit. But for water is much higher at 4.2. So its temperature fluctuates only a little bit. Alright, and that is why our answer is so much closer to the temperature of the water as it is to the temperature of the metal. Alright, that takes care of example number 5. Let's go ahead and move along next to example number 6. In this one, we're asked a very similar question. In this one, we're asked a sample of copper at 75 degrees Celsius is dropped into 50 grams of water at 10 degrees Celsius. The final temperature is 14 degrees Celsius. That is for both 14 degrees Celsius. What is the initial mass of the metal? And they give you the specific heat of copper is 0.092 calories per gram centigrade Celsius. All right, so let's write all of these values down first of all. All right, and I do have to add one more line because we are given the final temperature. So I'm going to write TF here and TF over on this side. So there we have it. A sample of copper at 75 degrees Celsius is dropped into 50 grams of water at 10. Who is the warmer one? The copper is. So I'm going to put all information for the copper on the left. The water is going to be on the right. All right, so the copper is at 75 degrees Celsius. Ti, 75 degrees Celsius, is dropped into 50 grams of water. That's water's on my right-hand side, 50 grams of water at 10 degrees Celsius, initial temperature of the water. The final temperature is 14 degrees Celsius. That is for the system. That's for both of them. So I'm going to put it twice, 14 degrees Celsius here, and their final temperature is the same for both. And given to us again is the specific heat of copper. So I'm going to write that down, 0.092 calories, not joules, calories. over grams cents degrees Celsius. So what do we put for the specific heat of the water? Well, in 4.2 joules, oh, no, not joules, we're needing calories. So how much is 4.2 joules in calories? The answer is every 4.2 joules is equal to 1 calorie. So you're going to see that for a specific heat of the water, 1 calorie per gram times degrees Celsius. All right, so there's all the data that we need, and we're solving for what was the initial mass of the metal. All right, so we're going to go ahead and plug in all these values and again simplify and get that answer. So let's go ahead and begin plugging in. So we have the M multiplied times the specific heat, which is 0.092 calories over grams times degrees Celsius, multiplied times Ti minus Tf. Ti is 75 degrees Celsius, minus a temperature of 14 degrees Celsius for the final temperature of the system. Next, the mass of the water, it is 50 grams, multiplied times the specific heat of the water, which is 1 calorie per gram times degrees Celsius. And then it's Tf minus Ti. Tf is 14 degrees Celsius minus an initial temperature of 10 degrees Celsius. So that's all the values that we've got. All right, so what we're going to go ahead and do first is, well, we're going to go ahead and start by simplifying this again. You just want to make it as simple as possible. We have both values inside of the parentheses, so that might be a great first step. So I'm going to go ahead and do that. I'm going to go ahead and subtract 75 minus 14. That's going to go ahead and give us 61 degrees. So I'm going to rewrite this. M multiplied times 0.092 times 61, that is the subtraction, 75 minus 14, is equal to 50 multiplied times 1. And 14 minus 10 will just give me 4 degrees right there. Subtract. Next, I'm going to go ahead and multiply everyone on the right. So it's going to be 50 times 1 times 4. That gives me 200. And on the left-hand side, 0.092 multiplied times 61 will give me 5.612. And the M, just bring it down. All right, next, what do? I want to go ahead and simplify. So I want to get rid of the 5.6. So I want the M all by itself. So I'm going to divide it by 5.612 on both sides. So that way I can isolate the M. So it's going to be 200 divided by 5.612 gives me a mass of, we're going to round it off slightly, 35.6 grams. And that takes care of example 6. Up next, let's go ahead and take a look at example 7. In example 7, we're asked the following question. A 100 gram sample of iron at 99 degrees Celsius is dropped into 150 grams of water at 5 degrees Celsius. What is the final temperature of the system? And the specific heat of iron in joules is 0.449. All right, now this problem is a lot like the first one that we did. That was example 5, where we're solving for the final temperature of the system. So let's go ahead and get to work on this. All right, so I'm going to go ahead and write down all the information that's given to us. And 100 grams of iron at 99 degrees Celsius. So write that down. Initial temperature, 99 degrees Celsius. Is dropped into 150 grams of water at 5 degrees Celsius. Next, we'll find the final temperature. So I'm going to put question marks on both of those. And remember, it's the same value for both. They both finish with the same temperature. The specific heat of iron, it is 0.449 joules over grams centigrade Celsius. Because I use joules for this one, should I use joules or calories? Well, you want them to match, so therefore I should use joules rather than calories. And in joules, the specific heat of water is 4.2 joules per gram centigrade Celsius. So that's all the information we need. We're going to go ahead and plug it into the formula. And again, simplify and simplify some more until we can get the final answer. All right, so M is the mass is 100 grams. Specific heat, 0.449 joules per gram centigrade Celsius. Initial temperature, 99 degrees Celsius, minus final temperature. That's the left-hand side. The right-hand side, it is a mass of 150 grams, multiplied times 4.2 joules times grams centigrade Celsius, multiplied times final temperature, Tf, minus initial temperature of 5 degrees Celsius. So that is all of our information. All right, next. I'm going to go ahead and begin by just multiplying these values right here so I can go ahead and simplify. So I'm going to go ahead and multiply 100 multiplied times 0.449. That's going to go ahead and give me 44.9. Multiplied times 99 minus TF. On the other side, let's see, 150 multiplied times 4.2 is going to go ahead and give me 630. Multiplied times TF minus 5. Alright, now I'm going to go ahead and distribute inside of the parentheses. So it's going to be 44.9 times 99. It's going to go ahead and give me 4,445.1 minus 44.9 TF. On the other side, it's going to be 630 times 5. It's going to go ahead and be 630 TF minus 3,150. Alright, so that's what we got after the distribution of these values into the parentheses. Now we're going to go ahead and combine like terms. I'm going to move the 44 over to this side and 3,150 over to that side. So let's go ahead and do that. On the left side I have 7,595.1. On the right side we have 630 plus 44.9 gives me 674.9 TF. Final step, I want to isolate the TF, so I want to have it all by itself. So I'm going to divide both sides by 674.9. And that will cancel out. Give me the TF, the final answer, so that'll be 7595.1 divided by 674.9. Our final answer is just 11.3 after a little bit of rounding off degrees Celsius. That is the final temperature for the system. And that is example 7. Let's go ahead and move along to example 8, which are the last from this section. And let's take a look at that one. In example 8, we're asked a 436 gram sample of an unknown metal at 101 degrees Celsius is dropped into 500 grams of water at 25 degrees Celsius. The final temperature of the system is 27 degrees Celsius. Find the specific heat of the metal. So we're going to go ahead and do that. Find the specific heat of the metal. Alright, so let's erase everything we've got here. And let's write down all the values that we've got. Now, I do know that the initial temperature of the metal is 101. That one's much hotter than the initial temperature of the water at 27. So therefore, the metal we're going to put on the left, the water on the right. Initial temperature was 101 degrees Celsius for the metal, 27 degrees Celsius for the water. Alright, sample. The initial mass of the sample of metal was 436 grams. And for the water was 500 grams. Next, the final temperature is 27 degrees Celsius. So that is for both of these. Remember, final temperature is the same for both. And we know that this is water, so therefore we know specific heat. Now, I didn't specify here, should we get it in Celsius, in calories or in joules? Let's go ahead and find it in calories. Alright, so for every 1 calorie per gram centigrade Celsius, we're going to go ahead and find this one, and our answer will be in calories per gram centigrade Celsius for a specific heat. Alright, so now let's plug in all these numbers in, and so for our answer. So we start with 436 grams multiplied times C, and here's Ti minus Tf, initial temperature 101 degrees Celsius minus 27 degrees Celsius. Over on the right hand side we have the mass of the water at 500 grams. Multiplied times the specific heat of water, 1 calorie per gram times degrees Celsius, multiplied times final temperature of 27 degrees Celsius, and our initial temperature of the water, that was 25 degrees Celsius, that was our initial temperature of the water, so it's 27 degrees Celsius minus 25 degrees Celsius. Alright, so that's all the information that's given to us, and we're solving for the specific heat of this metal. Alright, so we're going to go ahead and begin by working with the parentheses, because we have all the values. So we're going to go with 101 degrees minus 27 degrees Celsius. So it's going to give us a value of 74 degrees. So it'll be 436. Bring that down. Let's drop the G for a bit. All right, 74. Over on this side will be 500 times 1, and 27 minus 25 is just 2. All right, next let's continue to simplify this. So it's going to go ahead and be 500 times 1 times 2. That'll give me 1,000. And on this side it's going to be 74 multiplied times 436 equals 32,264 times the C, which will still bring it down. Next step, I want to isolate the C, the specific heat. I want it all by itself. So I'm going to go ahead and divide both sides by 32,264, 32,264, and that's going to give me our answer for a specific heat, which should be a decimal. Metals do have very low specific heat, so it'll be 1,000 divided by the 32,000. Gives me an answer of 0.031. We're going to round it off to that. 0.031 calories per grams 10 degrees Celsius. And that is our answer for example 8. This brings us to the end of the second unit of Unit 6. Thank you so much for watching.